Good morning, everyone. Welcome to the last open webinar of 2022. We have Dr. Syed Farhan Hasany, one of new researcher of the SUNUM family today. Dr. Syed works in advanced materials. Dear Dr. Syed, welcome to SUNUM again. The stage is yours. Would you introduce yourself to us while starting the webinar?
Thank you, Ms. Nokta, for your kind introduction. My name is Dr. Syed Farhan Hasany. I joined SUNUM a couple of months back. Before that, I was working as an assistant professor in NED University of Engineering and Technology, Pakistan. My research interests are largely in nanotechnology-based advanced materials, the environmental sciences, and respective applications. So let me start. Let me share my presentation. Okay. Not sharing. I'm not getting the screen right now.
If you want, I can share your presentation.
Yeah, if you can. Yeah.
Okay. Will you share or I can share?
I can share if you want. Yeah.
Okay. Yes, we can see your screen.
Okay. Can you see the screen? Mm-hmm. Actually, today's topic is about the non-covalent assemblies of iron oxide with methyl carbon and nanohybrids. My name is Dr. Syed Farhan. I recently joined SUNUM. So as we all know, that nanohybrids are the heterogeneous nanoparticles, which are the conjugates of covalent and non-covalent bonds in order to increase the methyl functionality as well as creating opportunities for next generation materials, including, you can say, biomedical applications, environmental applications, sensing behaviors in defense applications, and there's so many different applications. We can use nanohybrids because of their different phases, because of the interaction of different phases between two different type of molecules or nanomaterials. We can use them for many purposes. Today's presentation is aimed to investigate the formation mechanism of two polymorphs of iron oxide, namely hematite and megamite, with methyl carbon nanotube and respective conjugate nanohybrids. We all know that iron oxide has 16 different polymorphs existing on the Earth's surface. Out of them, only 3 are the major contributors for different and variety of applications, namely hematite, megamite, and magnetite. Where hematite is the largest ore present on the Earth's surface, whereas it is non-magnetic in nature. Megamite and the magnetite, iron oxide, are magnetic in nature, and they behave as a superparamagnetic, they show superparamagnetic behaviors under electromagnetic conditions when the size are reduced to 20 nanometers or less than 20 nanometers. For that purpose, they have a variety of applications like separation mechanism or magnetic separation techniques, whereas hematite and respective nanohybrids may be used for sensing behaviors and different type of industrial applications. Here we will going to discuss a little bit methodology, which is a wet chemical technique, largely or on a broad spectrum. I can say it's a modified solder process in which there was no surfactant have been used. There was no surfactant have been used, and it's been modified at the synthesis route, that the isothermal treatment was reduced to a very short period with an optimized heating time and heating temperature. For the purpose, we have a one-part process reactor assembly, which was synthesized for producing these nanohybrids. These nanohybrids can be produced by using a Waals CNT, which was actually modified or which was actually oxidized before using it in the process. So the reaction, the methodology technique was comprised largely of two main parts. That is the surface activation of carbon nanotubes by using a strong oxidizing agent, mainly nitric acid was used at 60 degrees Celsius for 6 hours, which was then the graphite material was neutralized, washed and dried for further application. Whereas the iron precursors were surface activated by mechanical stirring in an inert nitrogen atmosphere. In the second part, what we did, we mixed the oxidized multi-volt carbon nanotubes with the surface activated iron precursor in a ratio of 0.1:1 to in a inert atmosphere. The iron oxide precursor was nucleated, mainly post-nucleated by a weak base at pH 9 to make iron hydroxide nuclei, which were then washed, dried, and passed through different synthetic procedures, which involves dialyzation, gel formation, condensation, and isothermal treatment. The major contribution of all these steps are the size control of a nuclei, whereas isothermal treatment was a large contributor to control the size of the crystal, whereas to control the nature of the polymorph. The major heating time to prepare a Magimite multi-volt carbon nanotube nanohybrid was around 300 to 350 degrees Celsius. So if we increase the temperature, these nuclei of iron hydroxide will convert into another polymorph oxide. Or if we heat it below 200 degrees Celsius, they will remain as a magnetite. Where magnetite is a very unstable form of iron oxide, whereas Magimite behaves as a stable iron oxide polymorph with superparamagnetic behaviors. So we can control the temperature to produce different polymorphs of iron oxide here. The large difference or the main difference is the same in producing a Magimite multi-volt carbon nanotube versus hematite multi-wall carbon nanotube is the isothermal treatment, because in order to achieve a pure hematite crystals, we heat it at 500 degrees Celsius for 15 minutes, because we can call it a modified procedure of wet chemical synthesis, that it takes only 15 to 20 minutes to got a fully grown crystal structure of iron oxide. Huh? Where? Okay. Okay. So the Megamite multi-wall carbon nanotubes were produced by largely two major portions of synthesis, or two major steps of synthesis, which were included as surface activation and then forced nucleation, which will end by an isothermal treatment for different temperature conditions to obtain different type of polymorphs. Megamite multi-wall carbon nanotubes were later applied for lead separation by a magnetic technique using external magnet from the water samples. This is a pictorial presentation where you can see, starting from a raw multi-wall carbon nanotubes, we oxidize it, we introduce Megamite iron oxide, and then we separate lead from, we adsorb lead on the surface of these nanohybrids, and we separate lead from the water. These are a few of the characterizations. I have put them here, which includes XRD, microscopic techniques, magnetometry technique, and FTIR. As we can see, that the Megamite structure and the CNT structures got brought with the low peaks. It means that we have found a nanohybrid with a low size crystals of iron oxide. So by microscopic techniques, we found that we calculate the nanoparticle size of around 20 nanometers, whereas the crystal size was much smaller. It was around 15 nanometers. When we go through the magnetometry technique, we found that saturation magnetization, or the hysteresis group, is much stronger when we compared it with the Megamite. This is because of the CNT conductive behaviors, that we have got much stronger magnetic behavior being given by a nanohybrid. FTR was actually used to confirm the crystal structure and the hygroscopic nature of that sample. These nanohybrids were later used to remove the lead by using atomic adsorption technique. Atomic adsorption technique was involved with a lead cell, and we use different concentrations, different temperature, different contact time things, and we also check the reusability of these nanohybrids for multiple times. So the results shows that there was a 96% removal of lead by using these nanohybrids by adsorption and separation technique. And the reusability graph told us that even after the 5 cycles, the separation and the adsorption was around 80%. So it was a very good result. We found it, and we can use these nanohybrids even after 5 cycles as well. We calculate the Langmuir constant as well, whereas the kinetic data was described by pseudo second order model with a with the correlation coefficient of above 0.995. This is an application we have got for multi-wall carbon nanohybrids. In order to prepare hematite multi-wall carbon nanotubes, all the steps are very similar, but the isothermal treatment was a bit different because of the temperature conditions we introduced, and we heat the nuclei at 500 degrees Celsius to get pure hematite-based multi-wall carbon nanotubes. These hematite multi-wall carbon nanotubes were employed as a sensor for gas sensing application. We performed XRD for that. We did microscopic technique and FTIR similarly to find out the purity and the particle morphology of these nanoparticles. We calculate the application by using a cyclic voltammetry technique using a potential state, where we use 3 electrode electrochemical cells, standard 3 electrode electrochemical cell to carry out the electrochemical tryouts by using the nanohybrids electrode as a working electrode, whereas silver electrode as a reference, and the platinum electrode was used as a counter electrode. For the purpose, we produce 0.01 molar phosphate buffer at pH 7, and we found a linear correlation between the response current and the increasing concentration of hydrogen peroxide, which is because of the increasing reduction of hydrogen peroxide with the increasing concentration. As we can see here, that it starts giving us at the potential of minus 0.25, and with the increasing concentration, we can have a different response current time. So hematite based multi-wall carbon nanotube nanohybrid cannot be used in magnetic separation, but it has a different application like sensing application, and it can be used in different industrial application as well, and for the future prospective application as well. It can be used in a anode material for lithium battery as well, because of the higher conductivity of hematite and carbon nanotubes. Recently, these are two of my papers which have been published on these nanohybrids. And actually, we are still working on the electrochemical behaviors of hematite-based multi-wall carbon nanotube for different gas sensing applications. So here we use hydrogen peroxide as a main target, but we are still working on different gas sensing behaviors as well. Recently, I'm working in SUNUM in various smart textile applications, and where my main object is using wording called waste to wealth applications, where I will going to use smart nanoclays being developed from the locally available nanoclays, locally available clay material, and then they can be used to enhance the mechanical behaviors of the textile fabric, woven fabric. In addition with these nanoclays, I'm going to use a quantum dots as well to compare and find out the better solution for the textile industry in Turkey and around the world. Secondly, I have started working with the Mutlu Akku battery producers in Turkey. So we are focusing on developing anode material and different other applications for the next coming up lithium-ion batteries. So that purpose, we are trying to modify the graphite material with certain other oxide-based materials to find out their large cycles and to find out their large density as well. So at the moment, I'm working on the smart textile applications and to produce high density anodes for lithium battery cells. So if you have any questions, thank you for listening. And if you have any questions, you can ask me.
I have a question.
Yes, please.
About your the hybrid structure, hematite and hematite, multiple carbon monoxide, and how to control the phase of the hematite and hematite. You only change the synthesis temperature or environment as well?
No, actually, the environment was all of the procedures were done in the inert environment, and they all are similar. Only the temperature is different because we optimize these temperature conditions for 3 of these polymorphs that we can produce a pure magnetite around 150 to 200 degrees Celsius. If we and these polymorphs will change their phase when we increase the temperature from 300 to 350 into magmite.
Okay.
And after that, if we go further heating, up to 500, all of these polymorphs will convert into a hematite phase, which is the most stable polymorph of iron oxide. And it is stable up to around 950 degrees Celsius. So
okay.
it is, yeah. Just the temperature we change.
Okay, is it really stable? And
Yeah.
what is the place of I think iron oxide in the multiple carbon nanotube, or
actually it is it is a decoration on the surface of multi-wall carbon tube with the van der Waals interactions of the, we oxidize the multi-wall carbon tube surface with oxygen, and then we introduce these iron oxide materials, so they form interlayer interactions between each other. It is not a primary bonding, it is actually a secondary bonding, which is still is not being defined technically, but it is some kind of interlayer bonding, which is giving not very strong bonding, but intermediate bonding between iron oxide and carbon nanotubes.
okay. And another question, if there's no question about the XRD result, how to distinguish, to identify the peak, the hematite and magnetite, or the other iron oxide phases, and they are very close to each other.
Yes, technically, yeah, hematite. There's a difference between the hematite and magmite XRD diffractogram because they show the peaks at the same 2 theta value, but the two characteristic peaks are different. And the one is 30 and the one is around 35 something. They are different with each other. In magmite phase, the peak at 32 theta is almost one third of the peak at 35 theta. But in case of hematite, these peaks are very, very similar to each other. It's not like 1:3 ratio. It's like 1:2 or 1:1 ratio. So this is a major difference we can find out by XRD. Even we can we can differentiate between hematite and megamite by looking at their finished product color. The hematite is reddish brown in color, like a brick color, whereas the megamite is light brown in color. So you can distinguish by even looking at the color of the product that this could be hematite or this could be megamite. But by XRD, we can distinguish through these two peaks. And yes, definitely there is a very, very difficult task to separate magnetite with megamite. But if we go through further exploration, we can see that megamite and magnetite are different at 2 theta. There is a peak which is at 59 2 theta value, which is actually a megamite peak, and 59.7 is actually a magnetite peak. So we can distinguish by XRD because of that characteristic peak that this is megamite and this is magnetite. Even that you can see by color as well. Magnetite is different in color than megamite. It is dark brown in color, but megamite is it's light brown in color. So megamite is more stable, and you cannot keep magnetite stable for a long time. And I counted megamite stability for almost 1 year after being produced. So megamite is largely more stable when you keep it under controlled environment like desiccator or something.
Okay. Yeah.
Thank you.
Thanks.
I would like to ask a question.
Sure.
So thank you for your presentation. I would like to ask whether you check the leaching of the nanoparticles to the liquid phase, because they're not chemically bound to copper nanotubes.
Mm-hmm.
Did you check the leaching?
I didn't check the leaching of iron oxide, but in my future plan, I have to check the leaching as well. But because I found out from the literature that iron oxide don't undergo leaching for longer time, so I just left it because of
since it is not chemically bound to carbon nanotubes, it could leach for like real world application. Yeah. For real world application, it would be great to check that.
Yes, definitely, we will do it. Yeah.
Awesome.
Thank
Thanks.
you.
Dr. Syed, we have a question on chat.
Okay.
Can you see?
Yeah. Yeah, it may dissolve by if you change the pH. Actually, in a solder press process, we can force nucleate the iron precursor by even using HCl as well. We can either use a basic medium or we can either use an acidic medium. So basic medium will not show a very good gel formation during the synthesis process, but acidic base nuclei, they will show a very good gel being formed during the synthesis step. So definitely pH will go into effect. In every application, pH will definitely affect, because when we see the electrochemical tryouts, we worked with the pH buffer or pH phosphate buffer at pH 7. The pH was fixed in the electrochemical behaviors. But for the magnetic separation, pH has not so much effect.
So I would like to ask a question, since you brought the electrochemical characterization.
Mhm.
So you showed some CVs, and can you elaborate on them? So which sweep rate did you use, and which peak did you use to sense the peroxide?
Yeah, actually, these peaks are for different concentrations of hydrogen peroxide from a range 0 to 7 millimoles of hydrogen peroxide. So we can see here that the reduction is cited at minus 0.25 volt. So this is it's still in the process. So I just showed few of these results to find out, to show you that we are working on these as well.
Okay, so these reduction peaks are done at different concentration or different sweep rates.
Yeah, for different concentrations of hydrogen peroxide, like 0 at 0 millimoles, 1 millimole, 4 millimoles, and 7 millimoles.
Okay, and this reduction peak, does it correspond to the reduction of water or to the peroxide itself?
Yeah, reduction of water. It is a reduction of hydrogen peroxide into a water.
I see. But the peaks that you showed, I mean, the current and the concentration with the current slope, you show a positive current, so I was confused there. So is the peak that correspond, and the peak shows around milliamps and the detection is around microamps, so I was confused there. That's why I asked.
Okay, thank you.
Yeah, thank you.
Hi, I have a question regarding of the lithium ion.
Mhm.
And by the way, thank you for your well-prepared presentation. So we are currently working on the recycle of the lithium ion.
Mhm.
I mean, especially the battery, which is used for the hybrid cars for our models.
Right.
So have you ever worked, because yeah, I saw on the last lithium ion battery of the next generation. Have you ever done search or research on the recycle of the lithium ion? Or if we continue to work on it for recycle part, could we reach you or like?
Yeah, actually,
share with you?
I have worked on the development, but I have been through the recycling part as well. I have gone through the research literature as well. So if you want, you can reach me and then we can discuss it.
Oh, actually, I didn't see your email. Could you share in the text part? I will be appreciate.
Okay. I will.
If you wish, because I check all the page of the form, but I don't see.
You can find out my email from the SUNUM page as well.
You can write to me and I can forward to Dr. Syed if you want.
Okay, thank you so much, Mrs. Chelik.
Okay.
Any question? Thank you, Dr. Syed, for your presentation, and thank you all participants for your participation. I wish you a happy new year.
Thank you very much. Yeah, I wish all of you happy new year as well. And if you need me, you can contact me for any further discussion. Thank you very much.
Thank you.
Thank you.
Thank you very much.
Thank you.